This talk is about malicious peripheral devices that can compromise your machine and what we can do to prevent such compromise from taking place. So in this talk, I'm going to focus a little bit on USB. So I'm just going to give you a very quick summary. On the hardware side, there's a host controller, which is the master of the USB bus, and it's a device that's physically connected to the motherboard, perhaps via PCIe. And then we also have hubs. For example, your monitor may contain one, or you may have just a separate one, like an adapter like this. And finally, we have peripherals. And on the software side, we have drivers that control each of these hardware components. Now, devices can be malicious because they have been designed to do so, for example, Stuxnet. But also, firmware of benign devices can be modified by compromised machines, as was demonstrated by bad USB. Furthermore, government agencies have been known to intercept shipments and compromise devices with backdoors and malware. Now, with this in mind, here are a couple of ways in which malicious peripherals can harm your machine. So a device can issue a particularly crafted payload that exploits a driver vulnerability. Now, we all know that drivers are pretty hard to get right, so it's not surprising that this year alone, we've seen reports of 13 vulnerabilities already, and this is only for the Linux's USB stack. I mean, other peripherals and also other operating systems show a similar pattern. Another attack vector is direct memory access. So devices can leverage DMA to write anywhere in memory. And this is particularly problematic since DMA bypasses the CPU and also bypasses most software defenses. Now, to be fair, in the context of USB, this type of attack does require compromising the host controller or one of its drivers, but such compromise can take place. Another example is a device that just lies to the operating system about its identity. When it is asked, what are you? The device, obviously we all know that this is a flash drive, but the operating system doesn't know that, so it'll accept any answer. In this example, this flash drive is capable of getting keyboard access and can therefore have the ability to change passwords, install malware, or leak data. Sadly, raising awareness about the dangers of sketchy devices has not really proved to be an effective solution so far. One last issue is that communication sent on the bus is transmitted in clear text. So what's even worse is that USB 2 and below, hubs actually broadcast all messages to devices. So as a result, if a device is promiscuous, that device can eavesdrop on all downstream communication. And if the hub is compromised or if the hub is malicious, then the hub can inspect all traffic downstream or upstream, and it can even modify that traffic. So what can we do about these issues? Well, fortunately, there are a couple of really good solutions. So the first one is just to stop using computers. Now, another alternative is just to close all the ports. Now, this becomes a little bit problematic if you have a new laptop, because typically new laptops only have one port, and they share that for power as well. Both of these solutions promote isolationism, though. And instead, what we would like is we would like to enable control interactions in this adversarial world. But here's the thing. Our machine already interacts in an adversarial world every day when we're connected to the internet. You see, our machine already has logic that determines and verifies who it is talking to. It has logic to prevent eavesdropping and data tampering. And there are even tools that defend the machine from malicious traffic. So I think one question that we should be asking ourselves is, how can we port these solutions to the bus context? Now, one option, of course, is just to modify the motherboard, the bus protocols, and the hardware. However, we want to ensure that our proposal is deployable. So we don't want to modify want to have to modify the motherboard. We don't want to have to modify operating systems. And we definitely don't want to modify billions of peripheral devices that are already out there. Now, we could also install network security logic directly in the USB stack. But the problem here is that we need to ensure that the bus is kept at arm's length. So it cannot perform DMA or compromise low-level drivers that do, among other things, demultiplexing and deal with providing power. And while there's a lot of related work, and I'm going to discuss a lot of this later in the talk, I think it's fair to say that Cinch is the first work to respond to all of these questions. Cinch makes deploying network defenses natural in the bus context. And based on our security evaluation, we find that Cinch is effective at addressing the threats that I just described, although to be fair, it is not perfect. Our implementation of Cinch is backwards compatible, and is also portable. In particular, it works across completely unmodified operating systems. We tested several versions of Windows. We also tested Linux and FreeBSD. Cinch separates the bus from your machine and creates an interposition point where enforcement policies can be used to ensure safe interactions. Now, in the rest of this talk, I'm going to discuss how we actually build Cinch, the types of defenses that we implement, and the effectiveness and cost of these defenses. So I'm going to start by describing how we separate the bus from the rest of the system. So here's what our current architecture looks like. The bus is directly connected to your machine, so it has a chance to perform DMA attacks or issue malicious payloads. Here's an abstract view of what we really want. So we want to take the bus, and we want to make it remote. And then we want to reconnect it to your machine with some communication channel that is amenable to interposition. Now, one possible way to achieve this abstraction is to just simply use two machines. Now, under this proposal, we can just plug devices to the sacrificial machine, and then we can export these devices via some network. And then this is going to ensure that any DMA attack or attacks on low-level drivers only affect the sacrificial machine, and then we can interpose on all communication before it has a chance to reach the protected machine, which is the one on the left. Now, the obvious downside of this approach is that it requires two machines. So one might wonder, can we do it with just one? And the answer is yes. And I'm going to show you how we do it using virtual machines. In the paper, we also describe other possible instantiations. So usually, just a brief primer of virtualization, usually the way virtual machines communicate with devices is through a virtual device that is emulated by the hypervisor. Now, one of the reasons that the hypervisor emulates devices instead of giving direct devices access to VMs is that DMA-capable devices have access to all of memory, and this also includes the hypervisor's memory. Which means that if the VM were malicious and you were given access to the device, direct access to the device, then it could use the device's DMA ability to compromise the hypervisor. However, recent processors and motherboards now include an IOMMU, which is a piece of hardware that restricts where in memory a device can write. And so as a result, the hypervisor can give the VM direct control over the device without having to worry about the device being able to compromise the hypervisor's address space. So in effect, an IOMMU can be used to prevent unwanted DMA, which is a critical feature that we need in order to separate the bus. Now, we can revisit today's architecture and see how we can actually apply virtualization to separate the bus in a very natural way. So the first thing we do is we just instantiate both machines as VMs. And then we're just going to add a network between them, an internal network. And then we're just going to use the IOMMU to map the bus to the sacrificial machine. And so this gives us the precise abstraction that we were looking for. So now that we have this architecture, all we need to do is insert an enforcer that interposes on all traffic. Now, internally, this enforcer is really just a set of middle boxes or modules that will act on packets. And so these modules can be arranged in a chain, as I depicted here. So the output of one module can be the input of the next, or they can be arranged in parallel, so you can have multiple chains. And the design of the enforcer is inspired by the click modular router. So one of the benefits is that writing a new module and plugging it in is actually very easy. Now let's turn to the defenses that we can actually build on this architecture. So the first defense is just to ensure that devices interact with USB drivers in a way that is consistent with the USB protocol. To achieve this, what we do is we just go through several of the USB specifications, and then we write constraints on the different types of USB packets. And so these constraints cover packet formats, they cover individual fields, and they also cover packet sequences. And so one example of an individual field constraint would be ensuring that a particular value is not restricted or that proper encoding is used. And then we can use these constraints to build a state machine. And this is going to allow us to keep a history of the packets that we've seen so far. And then, given an incoming packet, we can decide if we want to allow it or not. Now, this is a very simple type of defense, but it is actually quite effective against many types of attacks. However, there are still exploits out there that follow every single line of the USB specification, and even while doing that, they can still compromise your machine. And this brings me to defense number 2. In defense number 2, the goal is just to keep a database of non-malicious payloads, and this is just going to be similar to the way antiviruses, firewalls, or some intrusion detection systems work. And then we're just going to inspect traffic, and we're going to look for matches in this database, and if there's a match, we're just going to reject the interaction of the device. So this is very similar to, say, Snort, but for USB. So one obvious benefit of this approach is that typically deriving a signature is easier than figuring out where in the source code a particular bug is. Another benefit is that it makes it possible for users and IT departments to react quickly without having to wait for OS vendors to release a patch. Now, the obvious downside of this approach is that we need a signature, so this is completely useless against zero-day attacks. There's also some tension between protection and compatibility. So on one extreme point, we can just choose to match every single packet and drop it, and this will prevent against many attacks, but this is not much different than just closing all the ports. So it's going to just ruin functionality. And then on the other extreme point, we can just let everything through, and that's going to retain functionality, but it's going to do nothing for security. And then finding a good balance between these two is actually quite challenging. And the last limitation, of course, is that signatures don't really solve the underlying issue. You know, one can still exploit the same vulnerability with a different payload. Our third defense is adding authentication and encryption to the bus. So imagine a scenario here where we have a trusted device manufacturer that installs a signed certificate into a device's firmware. So under this arrangement, it should be possible for the device to just prove its identity to your machine. So this will prevent other devices from masquerading as, I guess, in this case, this keyboard. Now, if we revisit Cinch's architecture, what we see immediately is that we still have problems since all the communication on the bus is in clear text and is unauthenticated, which means that a malicious hub can impersonate devices or it can eavesdrop on all communication. However, under Cinch, we can actually install TLS endpoints at the device and another TLS endpoint at the enforcer. And as a result, we can ensure that all communication on the bus is encrypted and authenticated. And then what we can do is we can add logic at the enforcer that, for example, disallows certain unauthenticated devices. For example, we might not want to have unauthenticated keyboards, but maybe we're okay having an unauthenticated device that only draws power. So you can have this kind of functionality. Now, notice that communication between the enforcer and your machine remains completely in clear text, and this is to preserve our goal of backwards compatibility. Now, a major issue is that existing devices don't really support TLS. So what we do is we just build an adapter. And one thing that we found is that this adapter is actually cheap and straightforward to build. And in the paper, we describe the details of how we build this adapter and how we actually create a TLS session without having to modify the USB protocol at all. Now, in addition to the three defenses that I've highlighted here, we also discuss others in the paper. So for example, we have a mechanism for logging and replaying interactions with devices. We also have a way of sending all bus traffic to our real-time remote server, perhaps for auditing. We also can export device functionality via a higher level protocol. For example, we can access a webcam feed using HTTP. So now that we've discussed sort of the types of defenses that we can build on Cinch, I can answer two questions. The first one is, how well do these defenses work, and what is their cost? So I'm going to answer these questions in the context of our prototype implementation. So in our case, the hypervisor is just Linux KVM. The enforcer is just a user-level process that is written in Rust. We built the TLS adapter on an ARM-based embedded computer, and all our exploits are implemented using a phase dancer 21, which is a device that can be used to emulate arbitrary USB devices. It's this device here depicted on the slide. So let's talk about effectiveness first. So we evaluated Cinch's defenses in three different ways. So each set of these experiments gave us a better understanding of the strengths and weaknesses of Cinch. So in this talk, I'm going to focus on the first two, and then you can find the third one in the paper. So the first experiment consists of implementing and testing exploits for many existing USB driver vulnerabilities. So the goal here was to get an idea of what would happen if Cinch had been deployed prior to finding these vulnerabilities. And what we find is that 16 out of 18 exploits were prevented immediately by an out-of-the-box configuration of Cinch. So we didn't have to install any signatures. We didn't have to do anything special. And the remaining two exploits, both of these which affected Linux, were actually able to compromise drivers in the protected machine. And the reason for this is that these exploits were fully compliant with the USB specification, and they mostly targeted really poor logic in the drivers. So it was very hard to prevent just with an out-of-box configuration. However, once we derive signatures for these exploits, we can actually prevent these exploits from compromising this and other machines in the future. We also conduct a three-phase penetration testing exercise to ensure that Cinch's effectiveness is not really a byproduct of us knowing the attacks ahead of time. And what we do is we introduce a red team, which is a group of people who are in charge of writing and testing exploits. And one thing to note is that the red team was not involved in the development of Cinch at all. So as we go through the phases, what we do is we disclose more information about Cinch to this red team. And the goal here really is to model an attacker that has ever greater knowledge of Cinch. And then the red team just tests their exploits on a machine without Cinch and a machine with Cinch. And what we find, I guess it's a bit intuitive, which is that as the red team learned more about Cinch, they were able to craft more intricate exploit that sort of bypass sort of the securities of Cinch. And then the second is that the red team quickly realized that exploits that respect the USB specification and that are polymorphic. By polymorphic, I really mean that the same exploit just sort of changes the payload on every run. So signatures don't really work for that. Those type of exploits cannot be prevented by Cinch at all. Now we can talk about sort of what is the cost of these defenses. And I'm going to answer this question compared to a baseline. So the baseline here is just connecting devices directly to your machine. So there's no virtualization, there's no TLS adapter, no enforcer, nothing. And then we run 2 experiments. So in the first experiment, we transfer a 1 GB file to a USB SSD. And then we report the throughput, the memory, and the CPU cycles used. And what we find is that under Cinch, throughput is 38% lower. And this is primarily due to memory copies at many points in the stack. Also, memory overhead is about 200 megabytes, which is mostly for the sacrificial VM. Now, this is high, but keep in mind that it is roughly on the same ballpark as having 1 or 2 browser tabs. The CPU overhead is also high. It's about 8x, but the absolute, so this is the relative overhead, but the absolute overhead is actually not that bad because the CPU cost of transferring a 1 GB file was not high to begin with. So for the second experiment, what we do is we connect the USB adapter, we connect a USB Ethernet adapter. So to the operating system, this looks basically like a network card. And then on the other end of this adapter, we just plug another machine, and then we do a ping test. And so this is going to let us measure the RTT between the 2 machines. And what we find is that we add about 2 milliseconds of RTT. And this includes all the encryption and all the processing logic. So we have the adapter here as well. Now, as I mentioned at the beginning of the talk, Cinch makes network defenses applicable to the bus, but it also inherits all of their limitations. So our signature module is not really effective against polymorphic attacks. In order to prevent devices from lying about their identity, we need either to identify trusted manufacturers, or we need ways to bootstrap trust. For example, another way would be to use a pairing procedure like the one found in Bluetooth. The functionality of devices needs to be augmented, or an adapter needs to be used. So that's another limitation. And finally, to make the bus remote, we require hardware support for virtualizing I/O. And while this support is available in most recent processors, it is not yet universal. Now, there's a lot of work that relates to Cinch in one way or another. I mean, aside from the entire field of network security, here are just a couple of areas. So one way to look at Cinch is as re-architecting the OS in a way that interacts with devices. So one work that is particularly related to Cinch is separation kernels. And in fact, we share the same view that separation and interposition are 2 critical properties to achieve secure interactions. Now, works on driver reliability are complementary, and in many cases, they're also composable with Cinch. And in fact, making drivers robust enhances Cinch's other defenses as well. Finally, hot plug and device containment frameworks are good ways of preventing unauthorized devices from connecting to your machine. And some of these frameworks can actually be implemented as modules in Cinch. However, Cinch does suffer from the limitation that it doesn't really have visibility inside of the OS. So the types of authorization decisions that it can make are very coarse-grained. And I think in the next talk, we're going to see the benefits of having access to this inside information. To summarize, Cinch provides backward-compatible and portable support for implementing network security tools to the peripheral bus. Cinch's enforcer is modular, and defenses are natural and easy to implement. And while Cinch is not perfect, we believe that it eliminates some attacks and increases the barrier for others. With this, I conclude my talk, and I'm happy to take any questions.
Rick Farrow. So how much do you expose to the user of the enforcer? Does it like logging what it's seeing? So it says, oh, I just saw this attack.
So it depends on the modules that are written in the enforcer. So The enforcer, the way you configure the enforcer is we have a configuration file where you can specify which modules you want to load and in which arrangement you want to load them. So which module you want to act first and so on and so forth.
And where do the enforcer modules run?
They run as a user level process in the hypervisor. So the
In
hypervisor is
hypervisor,
Linux.
yeah. Okay.
Yeah.
And did you consider the idea of exposing the user of the device to what the device was claiming to be? So in other words, if you plugged in something you thought was a storage device and it's really a keyboard, that it would actually announce, just as a matter of information.
Yeah, so we built a module like that into the enforcer where as soon as the device is plugged in, the enforcer asks the user, is this the device that you meant to plug in? And then you can say yes, no. But sort of the key decision of allowing the device to connect to the protected machine should be done before it gets a chance to connect to the protected machine, not during the connection process.
Sure, that makes sense. Okay, thank you.
Yep.
Amit Vasudevan, Scilab, great talk. Couple of questions. Number one, were you able to sort of apply Cinch to other buses? For example, something like PCI. So let's say you have a hard disk that's connected to a PCI bus, which is running a firmware which can do a lot of things these days. I was wondering if you have any experiments that you've done with such buses.
No, we have not experimented with other buses. I think that's sort of our plan right now.
Okay. Second question, the sacrificial VM that you use, how tiny can it be in terms of the footprint? I mean, I'm just trying to understand whether you need a full-blown VM or you could run it as an instance within the hypervisor itself.
So it basically needs to have enough of the USB stack to be able to demultiplex devices and then provide power initially to devices. So once you have, and also to manage hubs, once you have that part of the USB stack, then that's really all you need. And then you need a way to sort of encapsulate these USB packets into IP. We do TCP IP. So once you have those two things, that's all you need.
Sounds good. Thank you so much. Appreciate it.
We're running a little bit ahead of schedule, so if somebody else is awake and has questions, we have time.
Okay.
I have one. Maybe you mentioned this, but if you're in the mode where you provide authentication and encryption and you need a dongle, how do you prevent the adversary from sort of unplugging that and going directly into the system? I'm assuming that in that mode you require any connection to be authenticated?
So let's see. So is your question that the adversary is physically present?
Yes.
Or? Yeah, I think we do not provide any mechanisms to prevent the adversary from unplugging physically the dongle. But Cinch can have a policy that says unless the device is authenticated, just don't let it through.
Exactly.
So maybe that's a mechanism that you can use.
Right.
Okay.
Is there a question on the way? No question. No
Thank
further
you.
questions. Let's thank the speaker again.